Welcome to week 11 live session of molecular spectroscopy of physical chemist perspective. I am Arthapurva Chaudhary. I am a PMRA at IIT Bombay, chemistry department. So we are actually discussing this NPTEL session for last 10 weeks and today is the 11th session, live session. And actually we are going to have one official live session on the next Tuesday and one extra session also that PMRF team or the NPTEL team will notify to you soon. So let us come to the topic of the discussion. What are we discussing? Today we are going to discuss about the electronic spectroscopy part and where we'll start with the rotational fine spectra. What are those and what are the PQR bands and what is a Fortran diagram and all. And after that, we will see that for the previous few weeks, we are studying about the symmetry. So how can we use symmetry to understand the different electronic states or different electronic transitions in oxygen and benzene, these kind of molecules, and we'll end with solving the week 10 assignment problem. So let us start. With the week 10 lecture number 49, which was rotational fine spectrum. So as you know, as a rotational electronic spectra, first suppose this is your electronic spectra where these are your vibronic bands along, suppose this is your energy axis and this is your intensity, right? And suppose these are your vibronic peaks. Okay. So if this is a vibronic peaks and if you have to zoom into these vibronic peaks, so these are all vibronic bands. Okay. First, let me remind you that suppose these are electronic states, two electronic states, then they have smaller uh, energy. So these are vibrational levels inside an electronic levels, right? And the electronic levels are inside the vibronic levels. Okay, and there could be a lot more. So what I'm trying to say for now, we are using a Born Oppenheimer approximation where we are dealing only with the we have started dealing with the electronic and vibronic states, and from suppose we are getting something like vibrational bands like this, and we have a high resolution spectrophotometer where we want to zoom into these vibronic bands, then we might see something like from this band, something like this. So what are these? These are actually your rotational fine spectra, which actually now you can see in your spectra if you have a very high resolution spectrophotometer. So what is the actual origin of this? So if you remember what is the gap, energy gap between two states. So generally in electronic spectroscopy, we talk about 0 to 0, that is V0 to V dash is equal to 0. It is a 0 to 0 or band origin. But suppose right now we are discussing that what are rotational spectra, right? So the energy gap delta E actually is equals to, suppose it is mu bar, which can be written as mu EV, that is your band origin, okay, plus delta, this is your rotational energy, right? B is your rotational constant. Why we have taken B inside this delta, or why delta means the difference, right? So why we have taken B inside it? Because we are approximating right now that your uh, excited state, it is B single dash. In ground state, it is B double dash. And your what is the relation between a rotational constant and your bond length? So here we are approximating that your B dash is lesser than B double dash. Why? Because we are approximating at excited state, your uh, bond length is going to increase than what is there in the ground state. Okay, because of that, we are approximating that B dash is smaller than the B double dash. And due to that, we are taking a delta B value. And if we write it more explicitly, then we are going to get something like B dash J dash 1 plus B dash. Here we are actually looking at two vibrational levels. Here B equals to 0, B equals B dash, dash will be equals to 1 of our electronic states, and there are multiple rotational states, 0, 1, 2, like this. So we are saying suppose a transition is taking place from anywhere from here, then this is your 0 to 0 is your uh, band origin, and then the rest of it is your difference between the energy levels, right? Okay. Now, now let us discuss about your uh, so what can we expect from here? What are the selection rules for this electronic spectroscopy? Selection rule says that it is possible from singlet sigma to singlet sigma. One rule is this, and during this delta G can be anything plus minus 1. Okay, during this, and if delta J other else, what can happen? The delta J can be 0 plus minus 1, but you have to remember J equals J dash is equal to 0 to J double dash is equal to 0 is forbidden. Other than all is allowed. Because here delta J equals to 0, you will see that delta J is equal to 0 is allowed, but not like that. J dash is equal to 1 to J double dash is equal to 1 is allowed, but J dash is equal to 0 to J double dash is equal to 0 is not allowed. Okay. So with that, let us see that what could be the spectra looks like for this. So we have this delta E value, right? So let us see that for different values of delta J, what can we expect? Okay. So there could be three types of thing. PQR kind of band. Why? Because of delta J equals to 0, delta J equals to plus minus 1. So let us first start with the Q band, which is delta J equals to 0, right? So if, and we already know that delta epsilon, so delta J equals to 0 means J dash is unchanged. Means your J double dash and J dash is same. Means it is going from, so suppose this is 0, 1, 2, 3. So we are going to 0, 1, 2, 3, 4. Okay. So 0 to 0 is not allowed. Okay. But suppose we are going from 1 to 1, like that, or 2 to 2. This kind of case we are discussing. Then your delta, you already know the band origin is new, new bar AB. Then it is your B dash, J dash, J dash plus 1 minus B double dash, J double dash, J double dash plus 1. So if your J equals to J double dash, then we can write, right, that it is new B dash, J double dash, J double dash plus 1 minus B. So we can simplify it in one line. Why am I writing these many things? As we taking this B dash minus B double dash J double dash plus 1. Here J double dash can be 1, 2, 3, and 1. It can't be 0. Why? It can't be 0 because we already know for the selection rule that for delta J equals to 0, 0 to 0 is not allowed. So J dash will start from 1 to 3. What about P band? Let's see. P band is, delta J equals to minus 1. Delta J equals to minus 1. So delta P we can write new EV, comma V. Then, and that means here J dash minus J double dash is equal to minus 1. Right? So we can actually write in terms of uh, J dash. So J dash is J double dash minus 1. Okay. Or your J double dash is J dash plus 1. So, okay. So your this part is going to be remain as same, J dash plus 1 minus B dash double dash. J double dash is now J dash plus 1 and J dash plus 2. So I can simplify it a bit. EV B dash, and we can actually take common J dash plus 1. So I will do that first. I will take J dash plus 1 common, and then I will have B dash J dash, right? And from here I will have B double dash J dash, okay? And I have B dash J dash, state J dash plus 1 and taking common Bj plus 1 where I am writing B dash minus 2 B double. I can actually, so this part was not required. Sorry for this. I will just write all the things together. So this is actually B dash J double dash square plus B dash J dash minus B double dash J dash square, right? Now it is 2J plus 3J or 3BJ 1 is going to come. So that is going to give me okay. Let me do one. So J dash is J double dash. So what I'm trying to do that I'm trying to simplify my equation a bit. Much. So J dash is here J double dash minus 1 and J dash minus 1 is J dash. Then I have J dash plus 1 which will be J double dash, right? Because it is J double dash minus 1 plus 1 will be 0. Then I have B double dash and means what I'm trying to say is that I'm not writing this line at all. Is pi epsilon equals to UV plus B dash G dash plus 1 minus B double dash J double dash G double dash plus 1. So I'm replacing J dash is equal to J double dash minus 1 for this particular branch. Then I am going to get P double dash J double dash J double dash plus 1. So now I will break it down. B dash G dash square minus B dash G double prime. Then here I have B double dash square minus B double dash J double dash. And I'm going to have new EB plus B dash J. I will take this as common. J double dash, if I take that as common, then I am going to get B dash minus B double dash J double dash square. Then suppose I am going to get one minus then B dash plus B double dash J dash. So this is one of my equation, and here my J dash can only be C. So here what I'm trying to say is these two are my vibrational level. Then these are my rotational levels. Suppose this 0, 1, 2, 3, 0, 1, 2, 3. Delta j equals to negative means I'm going from 1 to 0, 2 to 1. Okay. In this case, see, I am starting, I can't go from 0. So my j double dash is 1. It can start from only 1, 2, 3. Okay. So, and what about, and what do you see from here? Your j double dash square for any value is going to be positive. But see, what I already told you, your b dash is less than b double dash. So for that, this is coming as a negative value, right? And if you think about this is the negative value is below before that, so it is also going to be negative. So negative and negative, and this is some positive. So your p band is going to come at lower energy wavelength, a lower energy portion than your band origin. Okay. What I'm trying to say, suppose this is your x-axis, band origin we can't see. So, but still, suppose if I write it like that, and this is your band origin, then your p band is going to come here, and r band we will see where it will come. I should not. This. Okay. You will see where the R band is. For R band, delta J equals to plus 1. Okay. That means your J dash is J double dash plus 1. So we already got this. I will write the first thing. B dash J dash J dash plus 1. J double dash J double, and this is B dash J dash J double dash plus 1 minus B double dash. Okay, I've just made a silly mistake. Yes. J double dash is J dash minus 1. So J dash minus 1, and this is going to be J dash. So if I again break it down, V dash J dash square plus J dash J dash minus B double dash B square plus B double dash C. So we are going to get new B band origin plus B dash minus B double dash. I will take common B dash square. Then we have B dash plus B double dash G dash. Here you will see your what kind I will use a different thing maybe. Now see, it is delta j equals to plus 1, so your j dash can be 0. You are going to 0 to 1, 1 to 2, like that. Okay. So for that, this is negative, but your j dash will start from 1 to 3. Okay. So you will see that your 1 to 3 it will go, right? So this is going to be a negative component, and this is a positive component. So these you can't say where this is going to be. It will look like a parabola, right? These are all parabolas, right? This is also a parabola. But here you are going to get only one side of the parabola. Here your R band could be in this side, R would be in this side of the band as well. So that actually we are going to look at through portrait diagram. So we'll portrait diagram, and from there we'll get an idea of band origin, this value band origin, and another thing that is known as band A. Okay. So for that, I will just take you to the origin software, and where we will plotted diagram is we will plot. So this is your, suppose for this particular expression we are going to take your b double dash, rotational constant as 8, and b dash is equal to 7.2. Right? So this is going for this particular experiment we are going to take. And J dash I showed you for this case it will be 1 2 3, and for this case J double dash can be 1 2 3. So we'll plot, and in x axis it will be uh, x axis will be your uh, new new bar energy, and as we are writing in terms of energy, right, delta E, and your y axis is going to be J or J dash, right, depending on which we are working. So in all the cases, actually, what we are seeing that we are taking J dash equal to 1, 2, 3 in all the cases. So it will not be a problem here. So let me draw once, and from there also we will try to get some idea. So let us start with Q band. Okay. What is the formula of Q band? Q band is the first one, where your J dash can be 1 2 3, right? Y axis we have written plus 1 to 20, and we are imposing that B dash is 7.2 and B double dash is 8 centimeter inverse. Let me at least write the units. So centimeter inverse. So we will see how this will look like. Suppose I am not writing the band origin. Band origin right now, suppose it's taken at 0. So we are trying to plot energy. That energy is actually delta epsilon minus your band origin. Okay. So this is 1 2 3. Okay. Now here what you will write as a formula, we will write it here. B dash, that is 7.2 minus 8 centimeter inverse B double dash multiplied by J dash, J double dash. Yeah, J double dash start from 1. So it is a B column multiplied by B minus 1. And this is going to give me my E dash energy, right? So this is actually energy or new bar you can say. And this is going to give me my J double dash. So if I see it in a band, how it will look like? It will look like this. This is my, suppose I'm writing it here, this is my Q band. Okay. Okay. How will my p band look like? So for p band, what equation do we have? P band we have b dash minus b j square. Then we have something in terms of j double dash also, but b dash plus b double dash. So I will do it once. So the formula will be 7.2 minus 8 multiplied by b j double dash square, so b multiplied by b, right? Then we have something, right? We have b dash plus, we have minus b dash plus b double dash, j double dash, minus 7.2 plus 8 b. So that will give us, so to specify the multiplication, then give me something like this, and I will take this to plot over this. Okay, and let me show it in a different color maybe. These are actually my p band. Okay, and see, we are only seeing only one half of a parabola right now, but let us see what we are going to get for the R band. Just copied the formula. The formula is almost the same, just a plus here, and it is giving us something like this. Let's change it. See, this is actually giving me a, a parabola kind of thing where I can see it is symmetric with respect to some point. Now, this is my P, this is my Q, and this is my R band, where they are trying to converge but cannot, is actually your band origin. I don't know if I will be able to write it here. I will use this test here. I will, this is actually your band origin at this point, and this is actually, if you have this experimental data, then actually the importance of this Fortet diagram is, if you have these bands, the bands from the electronic structure, and you know already the formula, then actually you can get the band origin, value of band origin if you don't have it from spectra. And this part is known as band head. Which part? This where should where this line is touching. So this is your band head. At band head, your this value, I'll show you what I'm trying to say here. So at band head, so what is your R band refers to? That is mu EV over plus B dash minus B double dash J dash square plus B dash plus B double dash J dash. And J dash can be 1, 2, 3, and so on. So your slope at that point with respect to your J dash is going to be 0. So that actually give you your, so what is that? That is your, so this with respect to your J, it is going to be 0 plus this will give you 2 into B dash minus B double dash into your J dash, and this will only give you B dash plus B double dash, right? So you are going to see, you are going to get some equation for J dash, that is B dash plus B double dash divided by 2 into B double dash minus B dash. Okay. From if you have the spectra, then from the Fertet diagram, you will be able to get the band head. Okay, from the R band, and from there you will get the value of J dash, where the band head is going to come, right? And from there, what you can do, that if you put the value of J dash here, right, and you know the value of your the rotational constant, then you can get your band origin even from the spectra also. So actually, why I have written like this? So we will use this on one of our upcoming uh, assignment problem. Now, after this rotational spectra, now let us go to the symmetry of the electronic states. Symmetry of the states. So, what does this transition moment integral? You remember, I hope. Transition moment integral is given by the a few products. Suppose this part is from the Frank Condon factor, right? From the vibrational part, V, it will determine only the intensity. Now this part is for the electronic spatial part, orbital part you can say, and this from the spin. The so now we are going when we are going to see a state, then to determine a state we will require the molecular orbital. So, suppose the symmetry of a state can be generated from the symmetry of the product of the product of the orbitals, molecular orbitals they are in. So that is something like suppose psi will be phi 1 into phi 2 into something, and that goes in where phi is my molecular orbital and this is my overall wave function. And this means the uh, symmetry of this will depends on symmetry of my molecular orbital 1, molecular orbital 2 multiplied by molecular orbital 3, and right. So in writing what we can say, total electronic wave function is a product of wave functions of MRs, right? So in other terms, I can use the phi term here for the same goes for the symmetry. So there are few rules if you, for this. If you remember that if your molecular orbital phi 1 is doubly occupied, then what is going to be the symmetry of this? Whatever is the symmetry of your phi 1, irrespective of that, if your molecular orbital is going to be doubly filled, doubly occupied, then it will be totally symmetric. So let me write down that doubly occupied MO. Suppose all the MOs are doubly occupied, there is no HOMO with unpaired electrons, then that is a totally symmetric. Now suppose your phi 1 and phi 2 are totally symmetric, but phi 3 there is only unpaired electron, all but one doubly occupied. One doubly occupied. Then symmetry of the state, electronic state, it will be same as symmetry of this unoccupied. And what if two electrons in two unoccupied, two non-degenerate are supposed to non-degenerate emos, then symmetry of the state is going to be direct product of the symmetry of the emo. Okay, but this is going to be the case for benzene. But we will start from a system like oxygen where uh, the electronic states are actually your configuration. The unoccupied emos, sorry, the unpaired electrons are in a degenerate MO. So we'll see what will be the electronic state for that. So that is case is electronic state of oxygen. Okay, that is your O2 homonuclear diatomic. So it belongs to the point group D sigma H, right? Now this is the character table. So if you, what is the configuration? Electronic configuration is is in MO, it is 1 pi u 4. Before that, there are other fully occupied MO, but it is 1 pi g. These actually is unpaired electron. These are paired. So what I'm trying to say, this is pi g, and this is here unoccupied, sorry, unpaired electrons belonging to the same degenerate pi g molecular orbitals. Okay, so the MO have their symmetry species is pi g. So what will be the case here? Also, we have to take a direct product for the state, right? So symmetry of the state, electronic state. So this is electronic configuration. Symmetry of the ground state. We are talking about the ground state right now, right? Is pi g into pi g, right? And if you do that pi g into pi g, let's see what we are going to get. I'll write here under the same symmetry operation. We are going to get 4 cos square pi, and then 0, and then 4, right? And then again 4 cos square pi, and then 0. Now, this is an reducible representation, right? By looking at that, but you can't use that formula that AI is equal to 1 by H um, sum over R pi of R into pi I. Why? Because here H is infinity. So anyway, you can't use this formula there. Okay? The total number of operation is infinity because there is infinite number of operation can be possible. So here we will use just a small trick. See that 4 cos square pi is there. So, and one more thing that all the, it is respect to g into g. So ultimately whatever you are going to get, it will have a g symmetry, right? So your what I'm trying to say. that all the constituent irreducible representation will have G. So this you can forget about these U things. You can forget. You need to look at only on these things. And another things you have that it is 4 cos square phi. You already know how to get that, I guess, right? Your 4 cos square phi is, so you know what cos 2 phi is, right? Cos 2 phi is 2 cos square phi minus 1, right? So 2 cos square phi minus 1 is 2 cos square phi is cos 2 phi plus 1. So 4 cos square phi is 2 cos 2 phi plus 2, right? So if you look at here, you have 2 cos phi here, cos 2 phi, and plus 2, 1, 1 will come from here. So actually you will see your this state actually not only this reducible representation has in terms of when you are writing states, you need to use this sigma plus G, then sigma minus G and plus delta G. So this is actually your ground state of the oxygen. But these are in two different, they are unpaired. They are in two different orbitals. So it is possible that your sigma G is in this could be singlet sigma plus G, and this could be triplet sigma plus G, right? Same for this, your it could be singlet sigma G minus or triplet sigma G minus. What about delta G? Same. It could be singlet delta G or it could be triplet delta. So possibility total number of state is C. Singlet means one state. Triplet means there are three possible spin states are there, right? So three states. So each of these they are constituting of 4 and a 4 8, and for delta you know it is 2 already, so they are going to constitute 8. So 8 and 4 and 4 will give you a possibility of 16 states. But you have two unoccupied electrons, right? In the place of 4. So 2 here, 2 here, 2 here, 2 here. So the way to the possible outcome is 4C2. The 4 positions are available and 2 electrons are there. So how many permutation or combination, how many combination you can use here to keep them unpaired and in two different states. That would be 4C2 and it is actually 6. So possibility is 6, but from here you are seeing that if you take all of them, then it is 16 states. So for that, you need to take care of the anti-symmetry principle, right? Which says that if your spin part symmetric, which is actually triplet, case for triplet, your special part should be anti-symmetric. Means your overall wave function should be anti-symmetric. And vice versa, that is your spin part is anti-symmetric case for singlet, then your special part should be symmetric. Okay. So from here we let us see that what is the case. So for sigma plus G, the special state, if you see it here, you are going to see that it is a totally symmetric case. So my special part is symmetric. Okay. For these two cases, sigma plus G, special part is symmetric. Then what is going to be my spin part? It should be antisymmetric. And spin part antisymmetric is possible only for singlet case, not the triplet case. So this is the possible state, not the triplet one. Okay. What about the other cases? In case of sig mm, case of sigma minus G, the second one, if you see, this is not a totally symmetric one. It has some antisymmetry with respect to C dash 2 operation. So that means it is not a special part is not symmetric but antisymmetric. Okay. If the special part is antisymmetric, then with respect to inversion, it is symmetric. If you see it here. But with respect to infinite number of those C dash 2, it is actually your antisymmetry. Then your spin part should be symmetric, and that is only possible for your triplet cases, right? What about delta G? Delta G, we don't have to look it for explicitly, okay? Don't have to look it for explicitly, but as you can see that for this also your uh, see how many states are remain. So this is the possible state another. So one singlet, one triplet, that means three are covered, three positions are covered, four positions are covered, only two are remaining, and you can only see this can be the another only possible case where your one singlet delta G, where your singlet state is antisymmetric spin part and special part is symmetric. So that is going to be your ground state for the oxygen. So in your ground state, oxygen, it is when singlet delta G. Okay. So this is the case for your oxygen. And what is the order of these means states, or what is the energy scale of these states? We will see this actually is at uh, So by Hund's rule, this will be your at the below, and this is then with the degeneracy of this state is high, so it will be a second, means that its energy will be higher than this triplet state, and it will be at the top. And I'm not going to deep. You can watch the video by Professor Dattarai. So there he has discussed how this singlet oxygen generation, or uh, how you can use this. So actually, your ground state, most of the state is there. So which is a triplet state of oxygen constitute of, and which is unreactive. But if you condense enough, or if you excite properly, then actually you will able to go to means you can generate singlet oxygen, which is okay, and that can be used in photodynamic theory and other thing, where on biomedical application of which is suppose for a cancer treatment and all. So you can obviously look at this from Professor Datta's lecture. He has already taught this. So whatever things are going to require for the assignment solution, I am helping with that for now. Okay. Now actually let us, as we have discussed this, so let us go to the possible electronic states for a benzene. Right. So benzene belongs to D6H, right? So uh, benzene. Here we will only talk about the pi electrons or p orbitals. So let us first draw how it will look like p orbital. So one of the p orbitals from Hokel-Lemo, I guess you know all these. So these are your p orbitals. The hollow circle means it has these have a positive low, and so this is the energy scale. Okay, and let me first draw all these things. Right. So here you are all. So here there is only one node, right? Actually two nodes. From node along nodal plane, and these are your homons. Okay. Why I will come back to this, because you have 6 pi electrons, right? So two will be here, two will be here, two will be here, and this is your homo, and this I am drawing will lead to a possible excited states, which can be your homo, and there is another one. I will draw all of them. Uh, Here your nodal plane should be 2, right? Um, so this is negative, this is negative, then positive, positive, then negative. So that is one possibility. Then This is negative. Okay. And the last one is alternatively negative. So I am showing you from the top view. These are top view. Below there is the negative plane. Here the negative part is on the top, so your bottom part is your positive one, right? So if you see a symmetry element for this particular orbital, so you will see it belongs to, if you obviously for E it will be plus one. If you go for a C6, it will not change in the positive sign, so for plus one. Then for C3, the same plus one, it will be symmetric for C2. Now this C2 is also along the Z axis, so that is also not going to change it. But what about the C dash 2, which is along the C2 dash, which is actually along the uh, atoms, then actually you are going to get a minus one. Okay. Then what about the C double dash 2? That if you think about it is going from the plane, this half of this bond, then for that also you are going to see that the sign will change. So it will be minus 1 till now, and then for obviously for inversion, this will go below and this will go below, so all the positive and negative will going to come. So that is going to be a minus, again anti-symmetric with respect to inversion. So what about sigma h? For sigma h also this is going to be minus 1. So we are going to get minus 1, minus 1, minus 1. And for sigma h we are also getting minus 1. So the state is actually, you can say this is actually equal. And also for these two, they are actually going to make, they are going to together, actually their symmetry is going to be 1G. And similarly for the LUMO, it is E2U. And for this case also you can check, it is going to be B2G. Right? So if that is the case, and if I, so what is my electronic configuration here? So electronic configuration become my like E1G 4, E2U 0 in ground state, right? So that belongs to which state? That ground state have all are filled, doubly filled. So A1G, right? Totally symmetric. What about this electronic configuration? One, when it has E1G 3 and one electron went to E2U 1, then this is the one of the excited state, right? So it is going to have a direct product. E1G belongs to E1G, okay, multiplied by E to U. So if you look at a product table, do I have it? I think I have it. I just have to go down here. Just copy it. So here what we are discussing, if you multiply E1G with E2U, so you are going to get B1U plus B2U plus E1U. Okay. Okay. And maybe I will E1G and E2. Okay. Now they belong to two non-degenerate state. So it could be either, so your ground state is A1G. Obviously A1G totally symmetric, special part. So your spin is symmetric, a anti-symmetric. So it should be singlet. And what about your excited state? It could be either singlet. And B1 plus triplet B2U plus triplet E. Okay, it could be either of them. So we already talked that your TMI is your psi V dash psi V. Then your orbital power comes into the play. Mu psi E and then your spin part. So we are now only dealing with this orbital part. So if we look at that, then we need to look at the psi E is the ground state, right? Psi E is if the transition is possible or not between the ground and electronic state, then you need to look at this psi E is. Mu could be either mu x, mu y, mu z. So you need to see that and your mu ground state, which is already we are saying that let me write in another color that it is A1G. So to be orbitally allowed, your psi es, which is orbital part of those, be fully allowed. So spin allowed to be then only singlet A1G to either of these three. The top one because they are singlet and they are triplet, so they are not spin allowed. Okay. But to be totally allowed, it is already spin allowed. Now to check this, you need to check individually that if it is going to be, uh, let me write it here, either. So, and one more thing, your XY, they together they transform into E1U, and Z is from character table we have this idea that they transform into E2U. Okay, so these are spin forbidden. Spin forbidden, if it is a spin forbidden, then the intensity will be very, very less. Okay, and if these are spin allowed, but we need to look at what state it could be the EA. So A1G, if it is A1G, then and for these to be non-zero, the direct product should be non-zero, or direct product, uh, no. What I mean to say that if the integral have to be non-zero, then the direct product is either A1G, or if it is a reducible representation, then or must contain A1G so that TMI not equals to 0. Okay? So you can see your B1U. Okay, B1U. So I will just copy paste this thing there. Uh, we are looking at psi ES, and then the symmetry of XY is E1U and A2U for Z, and ES is already A1Z. So we are looking not at the, leave the brackets alone for now, because we are not now bothered about the volume element. Now psi ES, we have option like B1U plus B2U, I guess, plus U1U. So I'll require the product table again on this page. Maybe I can click now. And if you see for B1U case, B1U, and we are looking at A1G, we will not consider E1U. E1U, that is E2G. Okay, so B1U into E1U is giving me E2G. Now we have B2U into E1U, B2U into E1U, B2U into E1U giving me same E2G, And what about E1U and E1U? They contain A1G. See E1U into E1U. So they will contain this. So this is also E2G. And 3 is E1U into E1U. That is the contain A1G plus A2G plus A2G. Okay. What about the other options? 4 that B1U into A2U or B2U into A2U or E1U into A2U. B1U into B1U into A2U is B2G and B2U into is B1G and E1U is E1G. So I'll write it here. It is B2G, B1G and E1G. Neither of them are. So these transitions are already we know that these are orbitally forbidden and these are also orbitally forbidden. Only this is as this contain a A1G, it is fully so first of they all had one here, right? Or fully allowed, which means obviously spin allowed plus orbital allowed. Okay. Now let me show you this. This is what we have come to that you singlet A1G to singlet E1U is fully allowed. Singlet A1G to B singlet B1U is spin allowed but orbitally forbidden. Singlet A1G to singlet B2U is spin allowed but orbitally forbidden, right? But we also know that orbitally forbidden processes can be allowed by vibronic coupling, right? What is that? During a so in all of these cases, we are approximating von Oppenheimer case. So if we see a breakdown of von Oppenheimer case, then approximation. So that will lead to um, so the TMI was something like the spin part was there, so I am keeping the spin part allowed. But now my vibrational state and electronic states are together. So if I read as mu psi e psi b. Okay, so I am considering this. So I cannot. Uh, so during vibration, when I'm talking about vibrational coupling or this breakdown of this von Oppenheimer case approximation, then my electronic orbitals and vibrational states are intertwined. So I cannot um, make them apart. So they are going to be on the same integral. So for that, what is going to happen again? We need to take the direct product of these. So to be TMI to be not zero, obviously we have talked about these are spin or spin allowed, right? So now if they are spin allowed, we are only talking about the orbital part and bichronic coupling. So your psi E dash, psi V dash, mu, psi E, psi V should not be zero. And for that, your triple product should be A1G or contain A1G, right? Again, so what about that? Does it have? So again, I will. So here, if you remember, your E dash is the excited state, obviously psi. And what is the symmetry of psi V? Here we are only talking about V dash is equal to 0 to V double dash. Sorry, V double dash is equal to 0 to V dash is equal to 1. So 0 to 1 transition we are only talking about. So your psi V is totally symmetric. If you remember our discussion from the normal modes of vibration, you will remember this. And psi V dash has a symmetry of xi, or you can say symmetry of normal modes of vibration. Okay, and you already know the symmetry of psi V dash. So and psi E dash you also know, and you know the symmetry of your. So here we are shorting it down that the direct product of 1 minute. हाँ बोल. हाँ पढ़ा रहा हूँ. आधे घंटे 1 घंटे में जाएंगे. क्या बोलता है? So what we are discussing is that your now we can simplify this whole thing into, suppose we are discussing psi e dash, psi v dash into your mu psi e psi v. So we already got to know that these two are A1G, right? These has a state of either uh, E1U or sorry or A2U. What about psi E dash and psi V dash? So psi E dash we already talked that uh, from E dash we already know that so I am taking psi V dash here, psi V dash here. So we already from our previous discussion we know what are these things are, right? Symmetry of this that is uh, I might write it mu xy together mu, right? So that we know is psi v dash. So this together we are discussing psi v dash. This was one case where it is uh, So here we can shift our discussion to here. So here what we are saying psi b dash, and this is our psi e dash into mu xy in all these cases. Here you can put your psi b dash, psi b dash. So if symmetry of normal of vibration either belongs to E1G, this is already allowed, this one, B2G or B1G, then all these which were earlier orbitally forbidden, those are going to be allowed by vibronic coupling. Okay, and let me change the slide so you will get the idea that these are orbitally forbidden but vibronically allowed by B2G and E2G, and B2G and E2G, and B1G and E2G can transform them into this. Okay. From there, we are going to discuss the spectra of the benzene that is right in front of you. That is the absorption spectra in y-axis is logarithm of epsilon molar extension coefficient. So from here, what we can see that these has this part. Actually, this is in log scale. So log scale, you can see the lower value as well as highest value. You can think of that as 10 to the power 5, it is 10 to the power 2, like that. So this part has a very high, as you can see, intensity. I should not say intensity because in observance it is intensity by intensity transmitted by incident, right? So this has a greater value of epsilon, which tells us that this is actually fully, this part is fully allowed, right? That means this is spin allowed as well as uh, orbitally allowed. This part could be orbitally forbidden, spin allowed, same about this part, and it has something over here what we will discuss it after a few minutes. So from there, we already talked that what are the vibrational modes are possible, vibronic modes that are listed here. Okay, and we are zooming into the benzenoid band. What is also, I am taking these slides from Professor Anind's lecture. So as you can see, this band is the hot band. Why? That's why it is written as H. What are hot bands? It generally the vehicles to one is not accessible at room temperature. Only at higher temperature it is accessible, so that you can see the transition from vehicles to 1 to 0 at higher temperature only, and that is why it is called as hot band. So you have a very faint hot band at the around 270 to 65 region, right? So that band is actually your hot band. And hot band actually here it is also shown from this energy E thing. You can see that this is your uh, V, this is your first energy level, and this is your second energy level, and this is your V equals to 1, and this is V equals to 0. This is your V equals V dash is equal to 0, double dash. This is double dash is equal to 0. equals to 0, this is equals to 1. So this is your 1 to 0, this is your this one. So that is your epsilon 1 to 0. And what about 0 to 0? That is your epsilon 0 to 0 is there. This gap is your delta, you can say mu double dash, and you can say this is your delta at excited state, the gap between the vibrational level 0 to 1 is delta mu dash. So where the dash is in the excited state, double dash is in the ground state. But for approximation, as Sarah has also taken, we are taking that delta mu dash is actually double dash is actually delta mu dash. So from there, what kind of expression we are going to get? That the epsilon 0 to 0 is actually epsilon 1 to 0 plus uh, delta mu double dash, right? And also another equation what you can get is uh, now you got to know that these energy bands energies are already given. So this energy is 38 point. So I will remove these points maybe for clarity. Okay. Okay. So this is given. So this is, so we are writing in a different format. So I'll write it here that your epsilon 0 to 0 plus the energy gap is 0 to 0 plus delta nu dash is 38,611 centimeter inverse. And here we are discussing that your if you, so this is your 0 to 1. So 0 to 1 is this band, right? You know it from here because 0 to 0, sorry. So 0 to 0 band will be somewhere here, but you can't see it because this is a band origin, right? Right? So this is your 0 to 1. 0 to 1 will have this, and 1 to 0 will have P0 minus 0 minus delta nu double dash, which is given 37.483. So from here, actually, we are assuming these two are same, and from there you can calculate your actually your E00 to be band origin to be 262.8 nanometer. It will come around that, and your this delta gap between these vibrational levels in excited state or in ground state is somewhere close to 564 centimeter inverse, which actually matches with one of these uh, normal modes of vibration, which belongs to E2 E2 E2G mode. That means only this transition, which was arbitrarily forbidden, that one, so this benzenoid band is due to this vibranically allowed by T2G mode, but Here we can't see any signature of B2G vibration. As you can see from here, 564 nanometer, B2G has something around 990 or 707 nanometer, close to that. So we can't see it in this spectra, right? So this is out of scope for this year, but you have to believe that this benzenoid band is vibronically allowed by E2G vibration. It is orbitally forbidden, spin allowed, but vibronically allowed by E2G band. Okay, and E2G band will. What did I write somewhere? Yes, I have made one mistake here. I don't know if we can erase it. Yeah. Should be E2G, right? Due to this E2G, E2G, B2G, B1G. This is already allowed. Right? Okay. So this benzenoid band is due to vibronically allowed by E2G band. And the B2G band is not there. And so what are these bands? So when this is the fully allowed, the blue band, that is around, that is for singlet A1G to singlet E1U, and the second, this one is for your 1A1G singlet A1G to singlet B1U. This was also orbitally forbidden, but vibronically allowed. This was done by some E2G vibration, right? And this is your benzenoid band. So benzenoid band is also weak compared to the previous one, but still in logarithmic scale you can see. But here the beauty of this, even though the signal is very low, but here the structured spectra are there from where you can get the 0 to 1 transition, those kind of transition you can all easily make out. So from benzenoid band, you were able to understand that this is actually the benzenoid band, which is a very famous or very used band in case of the aromatic compounds. It usually comes around 260 nanometer. That is actually a orbitally forbidden but vibronically allowed electronic transition. And the 350 region, what band you are seeing, that is actually a absorbance band from the singlet A1G to a triplet B1U. So this was what we were earlier saying. Na? These are spin, so spin forbidden, but these were actually orbitally allowed. Okay? So that's why it was the intensity is very less. But with that, uh, we are going to solve the week 10 assignment, and after that, we will stop to this session. Okay, let's start. So, for the first question, for naphthalene homo-lumo transition with inversion of spin is, so what do you, so for naphthalene, the case is going to be same as almost the benzene because the structure is, um, so this is for benzene, right? And this is naphthalene, two fused by. So it's the almost going to be the same. So with inversion of spin, that is your obviously that is going to be homo to lumo transition. Homo and lumo we have already seen for benzene, right? Here homo to lumo. So as you can see, spin forbidden transitions are actually not allowed. Orbitally allow, but spin forbidden. What about the second question? The states that cannot arise from ground state of electron configuration of O2, that also we have discussed in this part, right? Here, see, in O2,
only singlet sigma g plus is allowed, triplet sigma g minus is allowed, and singlet delta g is allowed. So the singlet sigma minus is not allowed. Singlet sigma minus is not allowed, and triplet sigma g plus is not allowed. Uh, rest of them are allowed. Also, oh, one delta G, singlet delta G is also allowed. Now comes a good question that this is why I was talking about the band rates. So rotational constant in an electronic ground state and excited state are given. So it is given that your B dash is 9 centimeter inverse, B double dash is 10 centimeter inverse. Band origin is given, which is your new V, that is given 18753. Find out the band age of the fine structure of the transition between two states. So if you remember the R band, which was new EV, right, plus B dash minus B double dash J dash square, right, something like this, and plus B dash plus B double dash J dash, where J dash starts from 1, 2, 3. Okay. Now this is given. This is 8753 centimeter inverse. Okay. But before that, I told you for a R band, here is your band head. So for band head, nu bar R by D J dash is going to be 0 plus B dash minus B double dash 2 J dash plus B dash plus B double dash, and J dash for that band head is going to be B dash plus B double dash divided by 2 into B double dash minus B dash. And this minus sign I have taken care of, and you are going to see this is coming as 19 by 2. Okay. See one thing, your J dash value is always going to be 1, 2, 3, and all. But in case of J band head, you are seeing this 19 by 2, which is not an integer. So your band head is coming at a position, you can't really see your band head also. Okay. Means if you think of it as a continuous line, then it, you will see it, but these are not continuous, right? J dash, these are all quantized. That is why J dash is 1, 2, 3. It can't be anything other than the integer 1, 2, 3, 4, like this. It can't, it is coming as 19 by 2 is 9.5. So that is not possible. It can be either 9 or 10. So you can't really exactly know it, but if you draw the R band, or you can get the spectra from there, you can have an idea that it could be like that. And if you put the value of J dash here now, so so your band head, so new dash band head is going to come at 18753. Now it is 10 minus 9 is 1 into 19 by 2 square, right? Actually, minus 1, 9 minus 10, and then B dash price is 19. 19 into J dash is also 19 by 2. So you are going to get something around 8748, 843.25 centimeter inverse, which is actually close to 1800, 843, and that is your answer. I hope you have understood this, and now we'll go to the next question. The next question is symmetry of states arising from the electronic configuration of a homonuclear diatomic. So that is again d sigma h, right?
and pi u1, pi g1 is the configuration. So here let us check pi. So pi u1 means one electron is this orbital, one is in there. So we are going to get 4, 4 cos square phi. Then we are going to get 0. Then we are going to get 2 minus 2 minus 4 minus 4 cos square phi, and we are going to get 0. And same process will follow. 4 cos square phi is actually here we will see from here minus 4 cos square phi. And one thing, you are multiplying pi g into pi u. So ultimately, whatever you are going to get, it will be u symmetric, right? Means anti-symmetric with respect to inversion. So you must think. So you can't use the formula here because the number of operation or number of order is infinite. So by looking at this, you also know minus 4 cos square by phi will be minus 2 cos 2 phi plus 2, right? So it is minus 2 cos 2 phi minus 1 like that. You from the previous idea, you have this idea that it would be sigma plus u plus sigma minus u plus delta u. It is going to be like that. So your sigma, it will consist include sigma u, sigma minus u, and delta u, not the pi. Yep. Now next question for nitrogen, similar homonuclear diatomic molecule. D sigma H again. The transition from 1 sigma g plus to 3 pi g. So your sigma g plus is already, so see, it is spin forbidden. From here we can see. So the answer is anyway going to be spin forbidden. Now we have to see that if sigma plus g, now here any of x, y, z or your pi z. So actually I should write it on the other way around. Here it is pi z, here it is sigma plus g. Okay, let us check again. So pi g is like this. So there is no xyz component. So okay, pi g into sigma g plus. So that is a totally symmetric one. So this is a1g. So you don't have to bother it about this. So only if either xy or z, if they are going to have a symmetry of pi z, then it will be orbitally allowed. But as you can see, the z is a1u and xy, they together are part of pi u. So xy together they are, so pi z, and xy is together eu pi u, sorry, and it is sigma plus a1u by u, and this is a1u, this is e1u, and pi g is actually e1g. As you can see, g into u is already going to give you some u, which will not be a totally symmetric, which will not contain totally symmetric, and for the second one also. So
So the direct product is not totally symmetric, right? And obviously, it is spin forbidden, so it is not orbitally allowed. So this is the right answer, orbitally as well as spin forbidden. Question number 6 for benzene, we have already discussed that A1G to B2U transition is orbitally forbidden. It can only be vibrationally allowed with the involvement of a vibrational of normal mode of symmetry. So A1G to B2U is only will be possible, and that is two things. Your B2U is this one. See, your B2U will only be allowed when it will have B1G or E2G. Why? Because yours when you only deal with the electronic part, not the vibronic part, you will get to know your symmetry of your product of symmetry of the dipole moment operator, dipole moment, and your excited state, electronic excited state generate B1G and E2G. So your excited state of the your normal mode of vibration should also have that, and that E1G and B2, B1G and E2G, B1G and E2G. Okay. Next, the well-known benzenoid band, as we already discussed, this is orbitally not allowed, but spin allowed, right? That is what we have discussed today. So with that, we are ending the discussion related to the electronic spectroscopy here. And from as you already, I think, have gone through the lecture, from lecture means week 11 onwards, sir has discussed. Means the next 2 weeks discussion is left. It is all about the NMR spectroscopy. So we'll do that and we'll try to solve some more numerical questions. And I hope today's discussion session was a little, I know it was fast, but I guess it was useful to you if you had any doubt regarding the lecture series and if you have any doubt regarding the um, assignment, especially with the band head and band origin, those calculation. I hope you will do it yourself. And with that, we will finish today's session. And thank you very much for joining and listening. Thank you. Thank you very much.